Hi, everyone. Welcome to the Spatial Machine Learning Explained Density-Based Clustering and Outlier Detection workshop. My name is Alberto Nieto. I'm a product engineer in the spatial statistics team here at Esri, and I'm joined by my colleague Xiaodan.
Hi everyone, I'm Xiaodan Zhou. I'm a product engineer in the Spatial Stats team in Esri too.
Great. So this session, we're going to focus on unpacking the black box of some of those really widely used methods in analysis and machine learning, such as those that detect clusters and outliers. We're going to focus on two tools, density-based clustering and the new spatial outlier detection tool. We're going to unpack how those algorithms work, take a look at how to interpret the results, and really get to apply them to solve some of the complex problems that you may face in the real world. So we're going to have fun and hopefully learn a little bit. Let's get started. So why spend an entire workshop thinking about clusters and outliers? Well, as geographers or really anyone that will ever consume a map, these two concepts are critical to how we interpret the patterns that we see. For example, your brain is immediately drawn to the patterns that you may observe in this map. The clusters, the areas with a lot of activity, or maybe the areas that are really sparse, the seemingly random outliers. And the next question may be, is it worth investigating? Is it worth putting our limited time and resources into clusters of traffic incidents, for example? So it's really important to have tools that help us quantify and evaluate whether something is indeed a cluster beyond what your eyes might perceive in a new map. And also, clusters and outliers are subjective. For example, in this map of traffic incidents in Los Angeles, a downtown area might have so many incidents and the population may be accustomed to those incidents that it takes a lot of incidents to trigger as a cluster, as something worth investigating. But if we navigate to a more rural area, a quieter neighborhood, the incidents are really not frequent, and it may just take a few traffic incidents in a row in a particular location to trigger as a cluster. So it's also important to have these tools that can understand the differences in these regions, in these neighborhoods, and their spatial densities when evaluating whether you have clusters or outliers. So this workshop is going to get into two concepts: density-based clustering, a tool in spatial statistics, and spatial outlier detection, a new tool in spatial statistics that we introduced in ArcGIS Pro 2.7. Now, the first tool, density-based clustering, is in charge of finding clusters based on feature locations. For example, you might have a data set like this that is scattered across space, and the tool's goal is to identify whether each feature in this data set belongs to a cluster or is part of random noise. Now, there are three different methods to do this, and the key difference between the three methods is the criteria for being a cluster. So let's take a look at how each of these work a little bit closer to see what I mean by that. Starting with the simplest, dbScan, the idea here is that you are defining what it means to be a cluster. The criteria to be a cluster are completely manual, in other words. And you tell the tool what it means to be a cluster using two pieces of information, two parameters. The first is the amount of features in a cluster, and the second is how far away you're willing to search to find that amount of features. So let's say, for example, with this data set that we tell it we need at least 5 features to be part of a cluster. The tool will take that and identify for a given feature how far away does it need to go to reach 5 features near it. And that defines what we call the core distance. That core distance is compared to the second piece of information that you gave the tool, the search distance, how far away you're willing to search for that amount of features. And then if your core distance is shorter than your search distance, these features define a cluster. However, if your core distance, the distance to reach the fifth nearest feature, is greater than your search distance, that feature becomes labeled as noise. In this case, this is really pertinent. For example, if you have a lot of information about what you're looking for in clusters. For instance, if you're looking at transportation safety, if you're trying to identify that that traffic signals maybe have a range of a few hundred meters or a few hundred yards in terms of how far away you can see them. You may not want to do clusters that are larger than that, so you may be able to pass that information as your search distance. Now, the second tool is called HDB scan. And the idea here is that the search distance is adjusted by the tool. You still tell the tool how many features you need to be part of a cluster, but beyond that, the tool really interrogates the densities of your data and adjusts that search distance based on what it sees in terms of the densities across different neighborhoods. For example, in denser parts of your area, the search distance will be shorter. So the criteria for being a cluster are really strict. You need to have a lot of features in a very tightly packed area to be a cluster. However, and then consequently in sparser areas, the search distance is increased, which makes the criteria for being a cluster less strict. You can have fewer features in a given distance to be a cluster. This can be really useful, for example, if you have a dataset that includes both cities and rural areas, and the denser cities have clusters in their context, and then the rural areas have clusters in their context. Now, the third option is quite interesting, and it's a little bit different. With this approach, the tool will first measure the distance to the next nearest feature, and that distance is plotted into what we call a reachability plot. This reachability plot contains the different distances that were measured. And if you look really closely at that chart, you have these peaks that emerge from the bottom of the chart that could be the starting point for a new cluster or for noise. And then the valleys, the features that have shorter distances between them, may all be candidates to be clusters, right? Additionally, this tool has a new parameter called cluster sensitivity. The cluster sensitivity lets you determine within clusters if there's additional peaks. For instance, that cluster in blue to the left now can be split. If you increase the cluster sensitivity, the peaks within that valley emerge and define two new clusters. So it lets you really tune the definition of a cluster and apply that to other parts of your study area. So in summary, we have three tools. DB scan, which uses a fixed search distance. It's really fast, and it's really meant to be a manual approach. You know what it means to be a cluster. HDB scan, which uses a range of search distances. It allows the spatial distribution of your data to really dictate what it means to be a cluster. And it requires the least user input. All you have to tell it is how many features per cluster. And finally, you have optics, which uses that reachability plot and the concept of neighbor distances. And it has a lot of flexibility for fine tuning. You can tweak the cluster sensitivity parameter to tell it whether you want additional clusters within large clusters. But it can be really computationally intensive as a result. So with that, let's get into a demonstration of density-based clustering. For this example, we're going to take a look at a data set of check-ins through applications on your phone. This could be a check-in to a restaurant or to a movie theater. Now, clearly this is older data. While people still go out and about, this is pre-COVID pandemic, so keep that in mind. But the idea here is that as you see this map, you may see some general patterns through the check-ins that people have made according to this data, right? And it's a lot of points on a map, and it doesn't tell us too much beyond the fact that they're in San Diego, California. So a pretty useful technique to start just exploring the distribution of this data is to run density-based clustering, which can be found in Spatial Statistics toolbar within the Mapping Clusters toolset. And here's the tool. So I like to just drag and drop our layers from the table of contents to our input point features. This is where you select one of those three methods that we talked about. I'm going to start with a simple DB scan, meaning that we're going to tell the tool exactly how many features per cluster. In this case, we want 100 check-ins at least. And you could surmise that, for instance, you may be looking at a new place to open up a store or a place to put an advertising sign based on the frequency of visits to those areas. So we need a lot of check-ins in order to meet that criteria. And then for search distance, how far away from that point am I willing to search for how many features are in there? I'm going to select 1 mile, and let's go ahead and run the tool. Now, while the tool runs, a quick tip that I like to repeat. There is a question mark here at the top right that not only gives you this nice little graphic that explains the tool, but also if you click it, it takes you to the tool documentation, which has a lot of information if you're curious about the algorithms and about learning more behind the scenes. So here are the results. Now, generally speaking, there's these large clusters that encompass most of the city of San Diego, but there are a few individual clusters that I find pretty interesting. For instance, zooming into this area, there's a mall with a lot of check-ins to that particular place that could be interesting if you're looking for retail analysis. Another example, if we go back out to the city as a whole, is farther south. This happens to be a really popular shopping area with a lot of strip malls and a lot of like a Target and different types of restaurants there. So this can be a useful first pass, particularly if you have a criteria for finding clusters. However, I want to change the setting to HDB scan, and in that case, you just tell the tool how many clusters, how many features per cluster rather, and then the tool will adjust that search distance. And for the sake of time, I simply want to show you what that looks like in our map. So if I activate that layer, if I turn that visibility on that layer on, the resulting clusters are a lot more defined, right? That previously large cluster that covered most of San Diego is now a series of smaller clusters. In fact, if we zoom into the San Diego Convention Center where user conference typically is held, you can see a few different clusters that start to give us a lot of information. For instance, you can see the convention center clearly defined by a cluster here, and that's actually separate from the Marriott Hotel right next to it. You also see the gaslight district or gas lamp, pardon me. And the gas lamp district, you have these different kind of regions within it. The shopping areas farther up north, the areas near the stadium, and so on. So this can be a really interesting way to almost find neighborhoods in social media check-in data. Finally, we have optics. So let's zoom back out, and I'm going to turn the layer on for optics. Now, optics is a little interesting in that you get a chance to see that reachability chart that we mentioned before. For optics, whenever you change it, whenever you run it with optics, you do have to think about the cluster sensitivity parameter. You can leave it blank and the tool will try to find an appropriate value for you, or you can set it and it's typically a value between um, 0 and 100. And with this reachability chart, what you can see is essentially the reason why these clusters were picked. So it's kind of nice to be able to explain why this area was clustered in addition to the map. For instance, if I select this valley over here, this happens to be this cluster right to the north of San Diego. And you can also see this gigantic monstrous cluster over here that was defined by, pardon me, let me select that one more time, that covered most of the city. It's very similar to the DB scan results from earlier. So what we could do is we could increase the cluster sensitivity, for instance, to something like 50, then rerun the tool. And I want to share with you what that looks like. So with that, we have quite a bit more definition here within that valley, right? We were talking about those peaks and valleys and the peaks being the key differentiators between different clusters. And now within this large valley, we see a lot of individual clusters defined here. So in conjunction with these charts, it can be a really powerful way to explain why your results are the way they are, why features were categorized as being part of a cluster or being noise. Speaking of noise, for the next section, we're going to switch gears to take a look at outliers. Now, inherently, you may think that outliers could be simply things that are not clustered, but in fact, it's actually a lot more nuanced than that because clustering algorithms really focus on the concept of a cluster and everything else is just simply noise, but there are actually further definitions within the concept of an outlier. And Xiaodan is going to take you through a few concepts and a demonstration of that. Take it away, Xiaodan.
Hi, I will demonstrate the Spatial Outlier Detection tool. This tool detects outliers in the dataset that are spatially anomalous compared to their neighbors. Although we can find outliers as a side product of the density-based clustering tool, this tool is very helpful when there are not necessary clusters in the data. In such cases, The main character of interest is outliers rather than clusters. In addition, this tool works as a pre-processing tool, for example, to exclude outliers from the data and ensure robust modeling in the next step. Here, I will demonstrate how this tool works. With these points in the space, we want to find the outliers, and we can do this in two steps. Step 1. We calculate a neighborhood area for each point based on how far out we have to go to reach a specific number of neighbors. For example, for point A, we create a neighborhood circle that covers the four nearest neighbors of A, which are point B1, B2, B3, and B4. And we can do the same procedure for all the other points. Step 2. We compare the neighborhood distance. We can see that point A is far away from its neighbors, while its neighbors, for example, point B1, are close to their neighbors. That is, the circle area of point A has lower density compared to the circle area of its four neighbors. In this case, point A is identified as an outlier. Let's take species conservation as an example. It's getting more and more common that scientists rely on the observation of the public to keep track of species. For example, on the iNaturalist website, anyone can contribute to the database by sharing their findings. Since the data come from multiple sources and non-experts, the website data manager needs to catch misidentified cases. The Spatial Outlier detection tool can facilitate this process. Here I have the California tiger salamander observations over years. This tiger salamander is an endangered species that deserves attention. I have 180 human observations up on the map. Now let's identify outliers in them. In the Spatial Outlier detection tool, I select the observations points as an input, set an output feature class and output raster. Users can also control the number of neighbors with a default of 20 and percent of locations considered as outliers. After running this tool, outliers are the orange points and inliers are the gray points. As you can see, there are outliers down in Santa Maria and in the valley based on the sparse distribution in this area. If we zoom into Salinas, a few outliers are identified because there are more clustered observations above here and out there. So the criteria for what becomes an outlier varies based on the distribution of points in that location. This is a powerful aspect of this method. In addition to the Boolean indexes that distinguish outliers and inliers, we give each point a score that evaluates how outlying the point is. The raster output visualizes the scores and allow the user to get a big picture understanding about the outlier pattern. If we open the chart, distribution of local outlier factor, we can select to prioritize outliers by the scores. With this output, the data manager can prioritize observations for data quality assurance, such as checking the salamander images. Without this, the data manager might have to start with a random observation. Another application is when field workers want to explore the potential unknown habitats of the tiger salamander. With this output, they can identify isolated observations and explore the nearby areas to see whether it's an actual habitat. In addition, say if a scientist wants to identify a research area that covers most of the salamanders, they can use the score map to narrow down the scope. For example, the area in green covers most of the salamanders. The default uses 20 neighbors to detect outliers. If the user thinks there are points should have been identified as outliers, and that doesn't match their domain knowledge or research context, they can decrease the number of neighbors, for example, use 10. With this new output, they can catch more outliers for their purpose. For purpose of identifying a research area, density-based clustering is a good candidate too. We try HDV scan with 10 neighbors with the same dataset. We will find that its outliers are similar to those from the outlier detection tool. This will be a way to validate the results. By making use of both the density-based clustering tool and the spatial outlier detection tool, the data manager can monitor data quality efficiently. The field worker can have good candidates of potential habitats. The scientist can narrow down the conservation area. That's the spatial outlier detection. Now let's give it back to Alberto.
Thanks, Xiaodan. Now, this is it for our workshop, but we hope you have a chance to try out these tools and that you share your work with us. Help us learn about the work that you do and how these tools can help your workflows. If you're looking for more information, esriurl.com/spatialstats has other presentations of this sort and also resources to help you get started. Additionally, we really listen to your feedback. So below this video, there should be a core survey that you can complete, and this will help us determine what kind of workshops we should have in the future. I hope you have a great day, stay safe, and enjoy the rest of your conference.